Hi, and welcome to Lecture 3. In this lecture, we are going to review the basic principles of the Laplace transform. The objective of this lecture is not to go over how Laplace transform is defined mathematically and how to find the forward or the inverse Laplace of a given function. That has been covered in calculus. The objective here is to see how Laplace transform is applied to control systems and what it represents. The upcoming lectures will all be based on Laplace transform and frequency response of a system. Thus, it is very important to understand how Laplace transform works and, most importantly, what a Laplace transform represents. The objective of this lecture is to review the principles of a Laplace transform and apply it to a given system. By the end of this lecture, you should have a good understanding of what Laplace transform represents beyond simply being able to calculate the forward or inverse Laplace transform of a given function. Laplace transforms have a variety of applications, especially in control systems. The reason is that most physical systems are governed by differential equations, such as this mass spring damper system. As we saw in the previous lecture, there is a distinct relation between the mass position and its time derivative. This is characterized by a differential equation. Looking at the electric system, we will see the same trend. There is a clear relation between the current, the integral of the current, and its derivative. The behavior of both systems is described by a set of differential equations, and the Laplace transform is a tool that we can use to solve these equations. When you're able to solve these equations, we'll be able to find a relation between the input and output of a system. And that relation in control systems is called the transfer function. In the mass spring damper system, the input could be the force F of t and the output could be x. But now if you have a temporal representation of the system, such as the one given here, it becomes very difficult to find that relation explicitly. If you're interested in the temporal response of the system, we now need to solve for that second-order differential equation. Let's cover the basic principle of a Laplace transform. We start with a set of differential equations that represent the behavior of a given dynamic system. The objective here is now to solve for x of t, which is a solution to that differential equation. By applying the Laplace transform of a temporal response, we now get the so-called frequency domain response, and by solving for the inverse Laplace transform, we can find x of t, which is the solution to the time domain expression that we started with. From now on, we will always study systems in the frequency domain. The process to model a system and solve for its temporal response thus includes creating a differential equation in the time domain, taking the Laplace transform of that differential equation, and hence creating the frequency domain representation of that same expression, finding the inverse Laplace transform that will give the solution to the equation that we started with. When you take the inverse Laplace transform, we are basically solving for the variable of interest. Now let's consider a mass spring system. Same as we had before, but now we are dropping the damper. The differential equation that governs the system is given in equation 1. It's a second-order differential equation. If you remember from differential equations, solutions to 1 can only have two forms. They can either be exponential or sinusoidal. The reason that the solutions can only have one of these two forms is that a derivative of an exponential is an exponential itself, but a scaled version of it. And the derivative of a sine wave is also a sinusoidal wave, but with a phase shift, and with a scaled version of itself. These are the only functions that have these properties. An exponential solution is characterized by exponential of negative sigma t, where sigma is a real number. By now changing sigma, we can create a variety of different exponential functions. The sinusoidal component is given by the exponential of negative j omega t, where omega is a real number, and this, according to Euler's identity, can be written as cosine of omega t minus j sine of omega t. And j is the complex variable. By now changing omega, we can create a variety of sinusoidal waveforms with different frequencies and phase shifts. The third and final possibility is that the solution to the differential equation is in fact a combination of both sinusoidal and exponential waveform. In this case, you can simply multiply a sinusoidal and exponential waveform and create a variety of different signals by changing sigma and omega. Put simply, the objective of the Laplace transformation is to find the values of omega and sigma that, once added together in this combination of both sinusoidal and exponential waveforms, will give the value of x of t, which is the solution to equation 1. As it is defined, the Laplace transformation is simply a multiplication of the original solution with a sinusoidal and an exponential component. The result of this is the representation of x of t, that is, the solution to equation 1, but in the frequency domain. Here is the standard definition of the Laplace transform. We have the original signal, that is the solution to the differential equation we are solving for. We have the exponential part of that signal, and we have the sinusoidal component here. The objective is to change the values of omega and sigma, create now a new signal using that sigma and that omega, multiply that new sigma with the original signal x of t, and take the integral from negative infinity to plus infinity. This integral can be seen as a way to compare how close x of t is to the new signal that we created by combining different values of sigma and omega. These two exponentials can be combined in one if you write exponential of negative sigma plus j omega t. And sigma plus j omega is what we define as s, that is the complex variable, the Laplace variable, which has a real part and a imaginary part. The real part now corresponds. Now the real part sigma corresponds to the exponential components that will form x of t, and omega corresponds to the imaginary components, that is the sinusoidal part of x of t. Here we have the standard definition of the Laplace transform, where the exponential can also be written as exponential of negative st, where s is sigma plus j omega. Real component and imaginary component. Exponential component and sinusoidal component. Let's assume that we have a signal x of t, and x of t is the solution to that differential equation for which we are looking for the Laplace transform. The Laplace transform is again a way to recreate x of t using a combination of different functions, different candidate functions that have different exponential and sinusoidal components. Let's call y of t a signal that we can create when we use different values of sigma and omega at the same time. As we change omega, we are now changing the frequency component of y, and as we change sigma, we are changing the exponential components of y. If sigma is positive, then the exponential component of y decreases. If sigma is negative, then the exponential component of y increases over time. And when sigma is 0, then the exponential of 0 is 1, and the signal then would only have sinusoidal components. What is the integral for? The integral represents how close x and y are. Let's take this 2D plane when one axis is sigma and the other axis is omega. Now let's pick a point on this plane. When you pick a point here, we are specifying a value of omega and a value of sigma. We can now create y of t as the exponential of negative sigma 1, negative j omega 1 times t. And this will result in a random signal that we created. Let's assume that that signal is this red curve. What do we do next? Next we multiply y of t with x of t. And when you take the integral, we are evaluating the area under the resulting multiplication. Let's assume, for instance, that this blue curve is now the result of multiplying x and y, that is the black and the red curve. When you now take the integral, we are adding up all the areas here. Because y of t and x of t don't match perfectly, the blue curve will have positive and negative instances. And thus, when you integrate now the blue curve over time, we are adding the positive and negative areas, and this will result in a finite number. That a finite number indicates that x and y are not very close. Now let's assume that we picked these 2 points, and these 2 points now have a omega 2 and a sigma 2. And you now create y2 of t as the exponential of negative sigma 2 minus j omega 2 of t. And let's assume that at this specific point, the resulting function that we created is exactly the same as x of t. When you now multiply x of t and y of t, the result is always a positive number. And when you take the integral of that curve, now we are evaluating a positive area. So the result will now be a very large number. And notice that that number, if finite, can never be greater than when x and y are the same. Now let's give our graph here a third axis, and let's call this axis x of sigma omega. That is the magnitude of equation 3. That is the result of this big integral. And now let's populate this graph for different points on the W sigma plane. We should see a trend that it will peak at a point where x and y match, where the signal we create by picking that point matches the original signal x of t. And it will be the greatest when x and y match perfectly. And these are the main points of interest. If you now have this 3D representation of the Laplace transform, these points where the Laplace transform tends to a very large number indicates that at that specific point of S, that is what we need to create x of t. That is the value of sigma and omega needed to recreate x of t. And these are the points of interest. This is a 3D representation of the Laplace transform, but most often we only look at two-dimensional representation because the only values that we care about are the values that will make the Laplace transform tend to infinity, to a finite number though, tend to a almost infinity number, or to 0. Those points that will bring the Laplace transform to almost infinite are called the poles of this function. And those numbers that will now make values here tending to 0 magnitude, if any, those are called zeros and will be represented by a circle. In this 2D representation, we now know that if you take this specific omega and this specific value of sigma, by putting that into the formulation for y of t, that is our probing signal, that probing signal is exactly x of t. And this is the first step to understand what Laplace transform does. Now let's look at a more concrete example. Assuming this LRC circuit, where an impulse voltage is applied to V, and the output of this circuit is the current I of t. For a given value of R, L, and C, the resulting current will follow an exponentially decaying sinusoidal waveform. We see that we have a sinusoidal waveform that is slowly decays exponentially. So I of t is made up with a sinusoidal and an exponential component. Let's further assume that the values of sigma and omega that recreate I of t are given in this graph here and correspond to point B. This means that if we take the value of sigma and omega at B, we can recreate I of t exactly. But to get there, to find out that B is the actual solution, we need to explore the entire S-plane, all possible combinations of sigma and omega. Now let's start with point C. If you select point C, we can create a signal IC of t as follows. At point C, the signal will have the same frequency as B, but the magnitude of the exponential component of C will be smaller than that of B. That means that IC, the signal that we create with point C, will decay is lower than the actual signal I of t. If you now plot I of t and IC of t, we'll see a signal with same frequency, but this signal will decay is lower. To do that, we can now take the integral of I of t times IC of t dt from negative infinity to infinity. We now multiply these two signals and calculate the area below the resulting curve. Because these signals are not perfectly the same, this multiplication will result in a signal having positive and negative parts. And when you take the integral, the negative parts will be subtracted from the positive areas. This will result in a small number that has no interest in the Laplace transform. Now let's look at point B. If you take point B to recreate a new signal IB, this signal will be the exponential of negative tau B plus j omega B of t. And we know that this is exactly what we need to create I. So if you now plot the signal IB, this matches the signal we have exactly. And when you multiply them, we have a curve that is always positive. When you take now the integral will be the area below that curve. And as you know now, because this is always positive, the result will be greater than the example we had with IC. And in fact, this will be the highest bounded number that we can have. Now let's look at a point A. If we now attempt to create a signal IA of t, A now has the same frequency as B and C, but the magnitude of the exponential component is much greater than B and C. This means that the exponential component will decay much faster than the actual response B. And if we now plot I and IA, we should see something decreasing much faster because the exponential component decays faster. And again, we are back in the same situation we were in C. The result will be a finite number that's smaller than the one we obtained in B. Now let's consider the point at D. At D, omega and sigma are 0, which means that the resulting function ID is simply 1. When you now multiply these two expressions, we are left with the black expression again, and we now take the integral of this expression. This will have all these areas added up, and over time, this gives 0. Here we identify three cases. The first case is a very large number, the second case is 0, and the third case are smaller numbers that have no interest in the Laplace transformation. These values represent points that don't match exactly the signal we are looking for, whereas a point where the signal goes to 0 is a so-called a zero of that signal, and points where the integral tends to a very large number are called the poles. Now let's assume that we scan the entire S-plane and the resulting function is given in this graph. We have two peaks which represent the poles of this function and 1, 0 where the magnitude of that integration goes to 0. What is the Laplace transform of that signal? Now that we have this representation, we can attempt to create a function, but now in the S domain, that will have the same behavior as the graph we populated in the temporal domain. In the temporal domain, when you pick the right S, the right combination of sigma and omega, the function tended to infinity. And when you pick the right numbers, the function also tends to 0. And that was given in the temporal domain. Now let's create another function, this time in the frequency domain, as a function of S that will display the same behavior. We want a function that when S approaches these 2 points, the function tends to infinity. And when S tends to this point, the function tends to 0. And let's call that function x of S. Let's start by looking at this point. At that specific point, the value of S is sigma is negative 15, and the value of omega is 0. So S equals to negative 15 plus 0j. When S approaches negative 15, the function x of S tends to 0. We can now define x of S as S plus 15. So when S tends to negative 15, x of S tends to 0, and that's what we see in this value here. We still have 2 more points to deal with. Let's start with this one. At that specific point, the value of sigma is 0, and the value of omega is negative 10. So S equals to negative 10j. When S tends to negative 10j, the function tends to infinity. How do we make a function tend to infinity? We can divide the function by a very small number. If we now divide this function by S plus 10j, when S tends to negative 10j, the function will tend to infinity. We have a last point here, and this last point, S equals to 0 plus 10j. How do we make the function tend to infinity when S approaches 10j? Well, divide the function by S minus 10j. To recap, when S tends to negative 15, x of S tends to 0, and when S tends to plus minus 10j, x of S tends to infinity. This is the exact behavior that we see in the graph, and this is the exact behavior that we get from the temporal definition of the Laplace transform. What is x of S? X of S is now S plus 15 divided by S squared plus 100. This can be written as s over s squared plus 100 plus 15 divided by s squared plus 100. We can now take the inverse Laplace, that is f of t, and this is cosine of 10t plus 15 over 10 sine of 10t. Understanding the concepts of Laplace transforms using a graphical representation may not be trivial, so let's try that one more time. Assume again that we have a signal x of t. This signal x of t is a signal that represents the solution to a differential equation, or is a signal that represents the output of a given system, such as the position of a mass spring damper system, the current, or the charge in an electrical signal. Because this comes from a differential equation, we know that x of t can be composed of two main elements. X of t can be a function of exponential waveforms, can be a function of sinusoidal waveforms, or can be a combination of them. Sigma is a real number. Exponential of negative sigma times t gives a exponential waveform. Exponential of negative j omega t, where j is a complex variable, gives a sinusoidal waveform of frequency omega. If you now take this signal, we can go from exponential waveforms only, when, for instance, omega is 0 and sigma is smaller than 0, or the other way around if sigma is less than 0, to a sinusoidal waveform when now sigma is 0 and omega is different than 0, to now combinations of them, such as this one, a combination of a sinusoidal and an exponential waveform. There is a sinusoidal that decays over time. In this case, sigma and omega are both different than 0. The question is, what is sigma, what is omega that we need to create x of t? Now, to do that, we need to create some signals and compare those signals with x of t. Let's call those signals that we create by using random combinations of sigma and omega a probing signal. To create a probing signal, let's pick a random point on this plane. We have here omega, the frequency, and sigma, the exponential component. Let's pick this point. If you pick this point, you're specifying sigma and you're specifying omega. Let's call this point A. So we have sigma A and omega A. With that, we can create a signal YA that is given by exponential of negative sigma A plus J omega A times T. This is the signal that we created. It could have any shape. Now we need to compare YA with X. How do we do that? That's where the integral comes in. If you now multiply these two signals, X of t and YA of t, and take the integral from negative infinity to infinity dt, this is a way to calculate how close these two signals are. Let's call the solution here to this expression, let's call that x of s. Now let's take our signal x of t that I'm going to try to redraw here. This is x of t. And let's take our signal YA. And let's assume that our guess here of picking point A to recreate X was wrong. So the signal that you're going to have is off, is not necessarily X of t. It's going to be something like that. This is YA of t. And let's draw around here the axis for time. And this axis here is the magnitude. What do we do now? Now we multiply these two expressions. You see that up to this part here, we have a positive number. Now x and y have different signs. This becomes a negative number. Here x and y are both negative, so you have a positive number again, and so on. And now we take the integral. Taking the integral means taking this area, adding to this negative area, adding to this one, and so on. The result here will be a finite number because y and x are not necessarily matching. The result is a finite number that has no interest in the Laplace transform. We can now give this plane here a third dimension. Let's call this x of s. And let's take the result that we got from this integration and plot that point. And that point here will be the xa. And now let's take this point A and make this point A travel all over the S-plane by taking all values of omega and sigma. This is accounted for in one step when you do the Laplace transform. Now let's go back here and pick another point. Let's A move to this location here. Let's call that point B. And by picking point B, we are specifying sigma, sigma B, and you're picking a omega, omega B. Now let's assume that this is the exact combination that we need in order to recreate x of t. When you take omega b and sigma b and put it in here, in our definition for yb in this case, yb is exactly x of t, is the same shape. Now let's draw the axis here. This is time, and this is the magnitude. Now they have these two signals, we can do the integral, multiply them and do the integral. Because the signals are the same, this is the same as taking the integral of x squared or yb squared. X squared or yb squared will always be positive. When you now take the integral, you see that you are taking the integral of a very large positive area. And the result cannot be larger than this one. The result now, because yb and x match, this will be the maximum value of this integration. Now let's go back here and plot the value. This value now will tend to infinity, though it will be a bounded number. So around b, we'll see that our function now will be tending to infinity. And because complex numbers always have a conjugate, we have another one here with negative omega. Now when we approach either of these points, our function tends to infinity. And if you now plot all points for all possible combinations of omega and sigma, we can see trends like this. This is the peak for B. At these peaks here, this means that at that specific combination of sigma and omega, we are approaching x of t. At all other points, the function will have lower values that have no particular interest in the Laplace transform. Another specific point that you need to pay close attention to is when this function tends to 0. There are specific combinations of sigma and omega that will lead to 0 in this integration. Let's think about, for instance, when x of t is a sinusoidal or an exponentially decay waveform, such as that one. And now when we assign omega equals to 0 and sigma equals to 0, y of t is simply 1. If you now take the integral of this expression, which is x of t, again, our new x of t, take this, multiply by 1, and take the integral, is simply this area minus this area plus that area, and so on. And this gives 0. When this is 0, we'll also see 0 there. So at 0, the function should tend to 0. Now that we have this representation, we can go back and try to find an equivalent S function that displays the same behavior. Now let's assume that after we did that calculation, we got a graph like this one. We have 2 peaks and 1 0. These peaks, we are going to call them poles, and the zeros, we are going to call them zeros. Let's assume that these peaks are occurring at a value of sigma equals to b and a value of omega equals to aj and negative aj. Now let's assume that the 0 is occurring at 0. Now I can take this 3D plot and convert that into a 2D plot with the location of these special points. So here we have the 2 poles, and here we have the zeros. Our function x of s was defined as the integral from negative infinity to infinity of x of t exponential of negative st dt. Exponential of negative st is what we use again to create the probing signals. Compare that with x of t through the integration. The result of that integration are points on this three-dimensional plane. Those points are the highest at these 2 peaks at the poles, and those points, and the result of x of s goes to 0 at that specific point when s tends to 0. Now, if you want to see what the function x of s is, we need to create a function of s that will display the same behavior as we see here. Let's start with points where the function goes to 0. In this case, the function goes to 0 when s tends to 0. How do we make our function now a function of s that it goes to 0 when the function tends to 0? Oh, let's just multiply that by s. So now when s goes to 0, x of s goes to 0. And we are here and here. Hypothetically, if that point was as sigma equals to negative 5, for instance, what would be here, then we would write s plus 5. So when s tends to negative 5, the function goes to 0. So this would be s plus 0 or minus 0. Let's look at this point. At this point, s equals to negative b. Right, this is the negative axis. Here, negative b, just to avoid confusion, negative b, plus aj. This is aj. Now, when s approaches negative b plus aj, we need our function to go to infinity. If you want this to go to infinity, we can now divide this by s plus b minus aj, or s minus this. S plus b minus aj. Now, when s approaches this point, this tends to 0, and x of s is s divided by something tending to 0, goes to infinity. What about this point? This point we also need to account for. At that point, s equals to negative b minus aj. Now, to make this function go to infinity when s approaches negative b minus aj, do s minus b minus aj. So we have here s plus b plus aj. Interesting. Now this function displays the same behavior as this function here. And this function is the Laplace transform of x of t. Now the way we approach this is not the traditional way we see in the textbooks. We went from having a signal to now decomposing that signal into this 3D representation here on the S-plane with the magnitude of this transformation, to having the Laplace function that represents that signal. But in reality, what are going to happen is that we have a model. The model will give us a differential equation. From the differential equation, we'll get here, once you take the Laplace transform of that differential equation. And from here, we'll go back there to create x of t. And this operation here, from going from the s function to the temporal response, is the inverse Laplace transformation of the function we obtained. With these definitions, we covered how to find the forward Laplace transform of a function f of t. The inverse Laplace transform is now the process of going from the function f of s to the function f of t. And this is done mathematically through this expression. But remember that the objective is the very same. Now we want to find the function f of t that recreates the same behavior as f of s. This will be very useful because these functions of s will later refer to them as a transfer function. They represent the ratio of the Laplace transform of the output variable to the input variable of a given system. And you can see that this can be very useful to find the relation between input and output of a given system. And as we discussed in lecture 1, this will be the first step to develop any control system. Now let's have an example here. What is the Laplace transform of f of t equals to 1? We can apply the definition of the Laplace transform. That will be the integral from 0 to infinity of f of t times the exponential of negative st dt. From calculus, the integral from 0 to infinity can be rewritten as the limit when a tends to infinity of the integral from 0 to a of f of t, that is 1, times the exponential of negative st dt. We can now solve for that integral easily as the limit when a tends to infinity of integral of exponential of negative st is negative 1 over s times the function itself, or from 0 to a. This is now the limit when a tends to 0, infinity, of replacing a, negative 1 over s exponential of negative sa. Now replacing 0 in the exponential gives 1, so minus negative 1 over s is plus 1 over s. And the result of this, when s tends to infinity, this term goes to 0, and the result is 1 over s. Luckily, we don't need to do this every time. Tables of Laplace transforms exist. Now let's find the Laplace transform of cosine of 5t, but at this time let's use the graphic representation. Looking at the function we're taking the Laplace transform, this is purely a sinusoidal waveform. This means that sigma is 0. We know the frequency of this sinusoidal waveform, that is 5 radians per second. So the peaks of our function should occur when s equals to negative 5j or s equals to positive 5j, plus 0 sigma, of course. If you now plot a cosine function and you take the integral from negative infinity to infinity, the result is the sum of all these areas, and this will give 0. This means that we multiply this function by 1, and to multiply the function by 1, our exponential of negative st needs to be 1. That is achieved when omega is 0 and when sigma is 0. These peaks are the poles, and the point where the integral is 0 is the 0. Now let's create a mathematical representation of what we just saw. We have a 0 at 0, if this is sigma, this is omega. We have a peak at 5j, another one at negative 5j, and a 0 there. Now let's create a s function that will display the same behavior. We want, let's call our function x of s, and we want x of s to go to 0 when s tends to 0. So simply we can write x of s equals to s. Further, we want the function to go to infinity when s approaches 5j. So now divide the function by s minus 5j. The function also needs to go to infinity when s approaches negative 5j. So divide it also by s plus 5j. If we now multiply the denominator, we see that the function is s squared plus 25. And this is the Laplace transform of cosine of 5t. The functions obtained in the Laplace domain will often be polynomials that are functions of s. Consider equation 15, where you have two polynomials, where a are the coefficients of s. Since we are dealing with real systems, we'll notice the degree of the denominator will always be greater or equal to the degree of the numerator, but never the other way around. If you end up having polynomial, it is very likely that these polynomials will not be found directly from a table of Laplace transforms. Thus, we need to split up a complicated fraction into small fractions that are readily available in the table of Laplace transforms. This is called partial fraction decomposition, and was also covered in calculus. The equation that we see here should be equivalent to equation 15, but now we have smaller fractions to take the inverse Laplace transform. And because we know that the Laplace transform is linear, the inverse of f of s, as we see here, is equivalent to taking the inverse Laplace of each individual fraction and adding them up. The objective of partial fraction decomposition is now to go from a complicated polynomial into smaller pieces that can each be solved individually, and because the Laplace operator is linear, we can add them up to create the time response of the entire function. Consider the first term where the factor in the denominator is as plus b. We can split that function into two components, c times as plus b plus g times gs plus e. The question now is what is c, what is g, that will result in the same original function. These are other terms in partial fraction decomposition. They all depend on the factor in the denominator. This has been covered in calculus and is just presented here as a reminder. Nevertheless, let's do one example. Here we have a function 3s plus 11 divided by s plus 3 times s plus 2. This falls in the first category that we saw in the previous slide and can be decomposed into a over s plus 3 plus b over s plus 2. If we now find a common denominator, that is s plus 2 times s plus 3, and you can rearrange this expression as follows. Now the denominator cancels and you have this equality. The question now is what is the value of a and b that will satisfy this expression? We can further expand this expression as, and from this we can now equate the coefficients of s from one side of the equation with the other. What multiplies s on the left side is 3, and multiplies s on the right side is a plus b. What multiplies s to the power of 0 on the left is 11, and on the right is 2a plus 3b. You may have learned how to calculate a and b using a different technique, and that is perfectly fine. This is just one of them. For example, instead of calculating it using a system of equations, we could have used a different technique. Here we want to cancel this term, so we set s to negative 2. That is 3 times negative 2 plus 11 equals to 0 plus b times negative 2 plus 3. And this also gives b as 5. And when we now set s to negative 3, we cancel the second term, and you're left with 3 times minus 3 plus 11 equals to a times negative 3 plus 2 plus 0, and so for a, which is negative 2. Both ways work. Now that we know the values of a and b, we can rewrite the expression as negative 2 over s plus 3 plus 5 over s plus 2. And the inverse Laplace of this, if you look at a table, is very easy to calculate. Notice something interesting. The values of s that will make this function tend to infinity are s equals to negative 3, s equals to negative 2. Real numbers only. Omega is 0. This means that the time response of that transfer function has only an exponential component and no sinusoidal component. This is exactly what we see here. Now let's do another example. Here we have a more complicated function. If you want to find the partial decomposition of this, because we have s plus 3 to the power of 2, we now need to expand this expression as a over s plus 3 plus b over s plus 3 squared. And because of the next term, s plus 2 squared plus 3, we need a third term, that is cs plus d divided by s squared plus 3. We can again find a common denominator. And you can now form a system of 4 equations and solve for a, b, c, and d. With these values, we can now find each of these terms in a table of Laplace transform and solve for the inverse Laplace. In this table, we have a few more transformations that can be useful. I recommend you find a good table of Laplace transform and stay with it until the end of the course so that you get familiar with the table. Again, the objective of this lecture was not to review how to do a forward or inverse Laplace transform, but rather what I want you to take from this is what the Laplace transform represents. Combinations of exponential and sinusoidal waveforms that, when put together, create a signal in the temporal domain that is a solution to a differential equation. We will use this concept throughout the course. Let's now do a few exercises on Laplace transform. These exercises will be posted in separate videos. Thank you.